You know, the equation we're decoding today, it really isn't just math. It is a fundamental law of physics, a mathematical coordinate transformation that literally powers almost every single piece of digital technology you interact with, from the way your smartphone compresses a video to the way artificial intelligence inherently understands human language. We are going to demystify the Fourier transform, and we're going to do it by fundamentally shifting exactly how you perceive data.
Information is hidden in frequencies. Just think about the weight of that statement for a second. Because in the time domain, which is how we normally look at raw data, like a microphone recording or a temperature sensor, everything is just a chaotic, intertwined mess. Complex signals hide their real patterns behind thick layers of noise. I mean, if you want to find a heartbeat in a noisy hospital monitor, searching through that raw time data is computationally brutal. The information is absolutely there, but it's hidden.
So, picture a perfectly mixed smoothie. It's this messy, raw wave of purple liquid, right? And your job is to reverse engineer the exact recipe. You obviously can't see the individual strawberries or bananas anymore. But watch how the Fourier transform acts like a magical sieve. As this chaotic, messy wave passes through our mathematical frequency filters, the data instantly rearranges itself into clean, simple, isolated sine waves. It essentially pours the smoothie through the sieve and outputs a perfect bar chart. Exactly this much 440 Hz strawberry and exactly this much 261 Hz banana. Now here is the absolute crucial point. The Fourier transform doesn't change the data. Not at all. It just changes the coordinate system the data lives in. The entire process is perfectly reversible. We aren't destroying or compressing the smoothie. If you take that recipe, those isolated frequencies we just found, and run them through the inverse Fourier transform, you mix them right back together to get the exact, untouched original signal back. We've simply moved the data to a place where we can finally understand it. Okay, so how does this actually work under the hood? Well, enter Euler's formula. This is the mathematical engine driving the whole thing. Now, without getting bogged down in dense proofs, just think of this equation as the actual sieve from our smoothie metaphor. It creates a complex vector that spins around a unit circle. The math is simply projecting our messy signal onto the spinning wheel to measure one very simple thing. How much does our raw data align with the specific rate of spin? And this is where the elegant logic of the discrete Fourier transform truly shines. If your chaotic data has a hidden wave inside it that spins at the exact same speed as our mathematical sieve, they align perfectly. The product stays positive, the sum grows massively, and that frequency reveals itself instantly as a giant spike. On the flip side, if that frequency isn't in your data, the spinning vector just randomly aligns positively and negatively, the sum cancels out to near zero, just silence. It is an incredibly beautiful, precise mechanism for isolating truth from noise. But historically, we had a massive problem, the naive DFT bottleneck. If you actually try to calculate these sums directly by multiplying an n by n matrix of complex roots, the math scales quadratically. Just one single second of high-quality audio at 48 kilohertz, that would require 2.3 billion operations. For early computer scientists, calculating this was practically impossible for large data sets. The magic sieve was just way too slow to be useful. Until a massive breakthrough changed the world. Think about the sheer computational contrast here. If you try to find patterns the old-school spatial way, the processing ticks painfully slowly. But when you leverage a brilliant divide-and-conquer trick called the fast Fourier transform, or FFT, the processing spins up incredibly fast. It is a blur. It turns painfully slow spatial math into simple, lightning-fast multiplication in the frequency domain. This is the convolution theorem in action. And honestly, it's an absolute miracle of engineering. That specific math trick, it gives us a 3,000 times speed up for that 1 second of audio, 3,000 times faster. It drops the required operations from 2.3 billion down to roughly 750,000. This single algorithmic shortcut is what transformed Fourier's equations from a neat theoretical curiosity into arguably the most important computational algorithm of the entire 20th century. All right, let's fast forward to modern artificial intelligence. If you're building models in PyTorch today, you use a very specific memory trick, the real FFT, or RFFT. You see, in deep learning, our inputs, like images and audio, they're pure real numbers. And because of the math, calculating the full FFT produces a top half of the spectrum that is just an exact, redundant mirror image of the bottom half. The RFFT simply exploits this mathematical symmetry to throw away the redundant calculations, which literally cuts your GPU memory and compute waste exactly in half. And this computational superpower is the unseen bedrock, physically building the modern AI tools you're probably using every day. OpenAI's Whisper relies on it to turn raw audio into spectrogram pixels. Fourier neural operators use it to bypass pixel grid limits so they can simulate complex fluid dynamics. Diffusion models rely on it to keep generated images from hallucinating weird artifacts. The Fourier Transform is quite literally the foundation of these architectures. Let's dive a bit deeper, specifically into large language models like Llama. Have you heard of Rotary Position Embedding, or ROPE? Now, it doesn't run the FFT algorithm directly, but it borrows its very soul, complex exponentials. It takes the query and key vectors of a sentence and treats them like a complex plane, spinning them. The low dimensions spin slowly to track words that are far apart, and high dimensions spin fast for words that are close together. Language models use the exact same fundamental laws of frequency to understand exactly where a word is located in a sequence.
And it gets crazier. Back in 2021, Google researchers took this to the absolute extreme with FNet. They proved that you can completely delete the famous attention mechanism in a transformer and just replace it with a simple 2D FFT. Because the FFT mixes sequence information globally, it acts as this lightning-fast positional mixer. It runs 7 times faster than standard attention. It's just a massive testament to how much raw, unadulterated power lies in frequency mixing. But all this power requires respect. What actually happens when we ignore these fundamental mathematical laws? Well, when engineers treat the Fourier transform like a black box, the mathematical reality of the universe fights back, and the results can be completely catastrophic for AI models.
The first trap you'll fall into is called spectral leakage. The math rigidly assumes your data chunk repeats perfectly forever. So, if you slice a chunk of audio and the ends don't align perfectly, you create a harsh mathematical discontinuity. Suddenly, a pristine, single-frequency sine wave registers as this fat, smeared, corrupted peak of false high frequencies. The strict solution here is applying a window function to gracefully fade the edges to 0, removing the discontinuity and restoring the sharp truth of the data. But the next failure mode, aliasing, it is so much more dangerous. Picture a rapidly spinning clock hand. If that hand is spinning super fast, but you only blink and sample it at the exact same rate it spins, it looks completely frozen, right? The high-speed reality folds into a low-speed illusion. In images, this creates jagged, corrupted moire patterns. In audio, high-pitched instruments turn into a muddy, low-pitched buzzing. If you sample data slower than twice its highest frequency, you violate the Nyquist limit, and reality itself aliases into hallucination. This establishes a hard, non-negotiable boundary for engineers. You absolutely cannot just raw downsample data. If you blindly ignore the math, high frequencies will violently fold into low bends, permanently corrupting the AI's training data. The strict solution? You have to apply an anti-aliasing low-pass filter in the frequency domain to physically cut off the dangerous high frequencies before you downsample. If you want to build a robust AI pipelines, understanding this math is literally a requirement. So where do we go from here? Because as powerful as the FFT is, we are literally already pushing past its limits. The classic FFT assumes a signal never, ever changes over time. We try to patch this with sliding windows, but that forces a really harsh trade-off between time resolution and frequency resolution. To solve this, the modern research frontier is heavily moving towards wavelet transforms, which use finite waves for simultaneous resolution. And we're even seeing learned Fourier features, where neural networks use gradient descent to dynamically invent their own frequencies tailored perfectly to the data. Let's tie all of this together with one final mental model. The Fourier transform is a prism for data. Think about it. White light enters a glass prism, and the prism doesn't change the light. It just separates the chaotic white beam into pristine, isolated colors. The Fourier transform is our mathematical prism. You feed it the chaotic, messy noise of the real world, and it perfectly separates it into the pristine frequencies that secretly govern our reality. Which leaves us with a pretty big thought to chew on. We've seen how just shifting our perspective from time to frequency completely unlocks our ability to compress images, simulate physics, and teach machines to understand human language. So if a simple mathematical lens can reveal the hidden structure of sound, images, and language, what other hidden coordinate systems are out there, silently shaping the digital world around you, just waiting for the right lens to be discovered?